Okay, everybody, let's get started. Today we'll be mostly focusing on interaction. So this will be kind of like we're one lecture behind now, but mostly today interaction. We'll do like an activity at the end. But first, I would be happy to take any questions that you might have about any course material covered so far with regards to the exam or any other logistical questions that you might have. So feel free to ask. Happy to answer. Yes. Here and Schneiderman, the interactive dynamics. Yes. Yep. Yes. No. I want to be fair because all of you have already studied over the weekend, I'm sure. And so yeah, what I'll cover today won't be in the exam. Sure. Let's go here first. You should be prepared by the homeworks, and you should refer to the course material related to D3, SVG, HTML at the beginning of the semester. Like, I'm not going to ask anything weird about maps or so, but about the principles of CSS, HTML, JavaScript, and D3. And the answers, like, you will be able to answer these questions if you review the tutorial pages. Yes. I'm not going to ask about like details, results of the papers, right? Basically, I'm going to check whether you read the paper in a way that you kind of understood what's in the paper, right? It's some kind of like high-level question about what is this paper about, what are the benefits of the methods proposed in this paper, and so on. Yes. It is timed in a sense that you have the time we have for this in this lecture hall. Usually people hand in early. It's not usually like a stressful thing to finish. But yeah, some people, like I would say usually a quarter stays here till the end. Yes. 5 to 6. And for undergrads, there will be one less. Yes.
You may have already answered. Will we be writing right in the exam, or?
Yes, it will be like a stapled test, like you probably got in high school, right? Yeah. So this is the same question that I just had answered earlier. I'm not going to ask you about the details, right? I'm going to ask you about the high-level stuff of the paper, right? Like, it's not going to be like, which is the better visual encoding compared between aligned bars and non-aligned bars. Like, that's not the detail, or what is the log error of those? This is not the kind of question, right? It would be the kind of question, like, what are the 3 types of interaction techniques, and how are they useful if you talk about the interactive dynamics paper, right? Or if, like, you know, think a little bit about what crowdsourcing is and so on if you for the other paper. Yes. No, you skip it. Yeah. Okay, well, if there's no more questions, let's talk about interaction. Let me just skip ahead. Okay, so I'm just going to recap quickly what we said last time because we barely got started with interaction. So we have when we do interaction, we have this, or like between static content and interactive content, there's the spectrum where like have static content would be things like infographics that you see on a static website, or even in printout or in books, and then you have dynamic content. And for dynamic content, we can distinguish between animated content, which is kind of like autoplay, but not user control. Like you can think of this as data videos, and we'll see a few of those really good examples later in the course. But here the user isn't in control, right? So there is no tooltip or there's no filters that you can apply and so on. And the second one is interactive content, where changes are the result of user actions. And interactive content is really like the most interesting piece. Like I should say that maybe newspapers tend to be somewhere, like modern newspapers, like on the websites, they tend to be somewhere between animated and interactive, or maybe even static, right? Like if you, for example, look at many New York Times visualizations, they might have nowadays a tooltip. There used to be a time 5 or 6 years ago where they were much more interactive, but there's been like a little bit of a trend for storytelling to reduce the interactivity, because it's kind of hard to get across the point that you want to make if you have completely open exploration, right? Whereas exploratory systems, like scientists would use them, they tend to be super interactive, right? Because there you don't actually know what's going on. So this is like an example that we looked at this New York Times visualization for these budget proposals, and the cool interaction here was to be able to dynamically facet by industry. So between those two pages here, between the left one here and the right one here. And that's the kind of interaction that you typically see in a newspaper story. But we interact with visualization because very often the data is very big and complex. So there's either two reasons. There's too much data to show it, and so we can interactively filter it down or reduce into a subset that we care about, or there are too many ways to show it, right? I could have different visualization techniques to show me interesting different aspects of these respective visualization of the data set. And so I might use interaction to link between them. And interaction also amplifies cognition. Like, you know, whenever you touch something, you understand it better. And the same is true on a computer in a virtual screen, right? If you can interact with it, you get a response. And so I showed the example of this interactive PCA plot just by exploring with the interactive plot and seeing what is the input, what is the output. You can learn something about PCA that would be hard to otherwise learn. And then we kind of stopped with talking about interaction methods, and you have to kind of like think about what you design for. So like we tend to like often primarily, like when we do a project here in this class, we tend to think about mostly mouse and keyboard. And that's kind of like a valid assumption as long as you stay in a professional context, right? But one reason probably why newspapers have reduced interactivity is because for newspapers, like the reality is a lot of people read a newspaper on a phone, right? Or on a tablet. And so people are lying in bed on their phone, and then they don't have their mouse pointers for highly precise interactions. And so you kind of like need to think about who are you designing for? What is your audience? What are their devices? If you have touch interaction on a mobile phone, you have to design very differently from if you have a mouse and keyboard interface that you can assume. And then there's like advanced things like gestures, as we saw. Gestures in this video, gestures are very imprecise, right? They're tricky to get right. Like there's also requires still a lot of hardware. Eye movement is similar. It's kind of like an interesting modality, but it's really hard to design for it because there's this phenomenon that's called Midas touch. Like you remember this the story that King Midas, everything that he touched turned to gold. And likewise, you can't really look at something consciously. Your gaze moves around. And so if you, for example, were to implement selection based on looking at something, you could actually, like, people will just involuntarily select all the time. And speech is actually quite interesting. There's now a fair number of kind of like, you know, with all of these language models, there are very good visualization approaches that where you can instruct a tool what to plot and what to show, and this will generate a plot for you, right? This is kind of like cutting edge research. And so I think speech and text input for visualizations is going to become more interesting in the future. And so we looked at this video here, but I want to skip this because we already did. And then we also looked at this gesture interactions for phones. And so that's kind of like the recap. Now I want to talk a little bit more about new stuff. And so one principle in interaction is direct manipulation. And so, like, for example, if you have a filter somewhere and you have a slider to adjust that filter, that's like a GUI widget, that's easy to implement, but it's very indirect, right? You have like your screen that plots something, and then you have the slider on the right that controls it. And the opposite of this is direct manipulation when you interact directly with an object, and you get continuous feedback and updates. And that's kind of like the gold standard that we want to strive for. So here is like an example, like from Jacques Bertin, the cartographer who developed this first list of the marks and channels that I showed you. He also thought about like data visualization with direct manipulation. But of course, he lived in the 60s, and there weren't really any interactive computers. So what he came up with was like a reorderable matrix that had like essentially these wooden colored blocks that had data on them, and then he could reorder them, right? And so in that way, he could kind of reveal interesting patterns in the matrix. And you could actually take out these steel rods from the rows and put them in the columns, and so you could reorder the columns. And so this was kind of like an early prototype of kind of like direct manipulation. Nowadays, of course, this is all very easy. For example, here is a typical example of a set of scatter plot matrix brushing. Like this is something that we now, based on last week's lecture on brushing, we could also implement. And notice that like I define a brush here, and it is directly in the same space as the data, right? This is the direct manipulation piece. And if I drag it around, it gets highlighted and it's all reflected immediately. If I had a slider here for X and a slider here for Y, and I would change those, that would be indirect manipulation, right? And clearly, like if I can do this directly in the same space as the data, it kind of like is much more intuitive to use. Okay, so there are many different ways of how you can interact and where interaction is useful. There is kind of like the single view and the multi-view paradigm, and today we'll be focusing on the single view pieces. The multi-views is the next lecture. So next lecture, we'll be talking about what if I have two displays of data that are synced in some way, how can we interact with them? What are the kind of the paradigms there? That will be like Tuesday in 2 weeks. And today we'll be talking mostly about single view in types of interaction. And so the big ones there are change over time. So for example, if I make any kind of change to a chart interactively, then navigation, semantic zooming, filtering and querying, and then focus and context. And so I'll go into those in detail now. And so now this is like the reading that you were supposed to look at. This is like the interactive dynamics for visual analysis. I don't want to go into too much detail here today, but this paper is kind of like a very gentle introduction into this topic, right? And so they kind of create this taxonomy for what are the purposes of interaction according to their view. And it was like this data and view specification. It was view manipulation and process and provenance. And so data and view specification is all about like selecting what is being shown on a screen. The view manipulation is things like navigation, coordination, organizing, and then process and provenance is a little bit, let's say, more abstract. These are things like recording, annotating, undoing, recording provenance, sharing, and so on, or guiding people through the analysis session. So these kind of like the first few here are the ones that we typically think of. And then the third one here is kind of like the more advanced thing. Okay, let me just quickly look at my mouse pointer isn't really working. Yeah. Okay. Great. Okay, so we'll start with change over time or transitions. And so the first question we want to ask is, why do we want to change a representation on the screen, right? Well, different representations tend to support different tasks. Think about, like, if I have a bar chart, I can either make it stacked or grouped, right? Or I can change the ordering, the layout, or the mapping. And transitions tend to make it possible for users to track what's going on. And so I'll show you two examples. First, there's like a simple tabular data visualization that I and some colleagues published a few years ago. Here, if you care about soccer, you might recognize some of the names here. This is like a list of soccer players. So you have the players, then their clubs, their position, whether they're left or right-footed or play equally well with both feet, their age, their height, and their goals, right? And so here, this is like a table, and I can scroll it. This is kind of like the first interaction here, but we can also dynamically change this table. So for example, I can sort it. And now by having sorted it, right, I can immediately see who are the people that shoot the most goals. And in this data set, it's Ronaldo and Messi, not very surprising, right? Or I could do something like change a single bar, like these two bars here separately. I could make them into a group bar chart, and then I could sort them based on that, right? And so now I've completely created a different visualization. I've kind of actually created a derived data set that lets me answer a separate question. Another example here is this tool. This is like essentially information about single nucleotide polymorphisms. It's not that important what that is, but this is like a biomolecular concept. But the idea here really is that you can plot this here, like this is chromosomal coordinates here on the x-axis, and then you have these SMPs here, and then you see kind of like some like bands and ribbons between them. And so at first, what you see here is just a 2D view, but then you could kind of like change the 2D view so that you have like even spacing. So here we kind of like changing the representation slightly. Then we can do some quantitative representation here, or we can go into a 3D representation, right? Or we can do a 3D representation where we encode another dimension here in the depth. Or we can now kind of change this into a completely different chart and look at the recombination rate from above, right? So these are all possible transitions that are basically the same chart, but just different ways of looking at it, where we use interactivity to reveal those differences. And sometimes this change over time can be very literal. So this is like actually one of the best projects from a few years ago from the class. This here shows how the railroads were built in the 1800s and how it influenced America. And so here, the change that we can see is literally the change over time. So I can like navigate here to different years, and I can do this even with the cursor. And like at this point there, we see there isn't really much railroads. There's some on the kind of the far east coast, but now we see the first railroads being built here in the year 1840. And then we see like new states being added to the United States. And then we see the development of railroads. And the railroads really kind of like, made it possible to move inwards and westwards. And then we had the Transcontinental Railroad connected here in Utah, of course, in the year 1870. And that kind of really transformed. And now we have like a fairly like sophisticated railroad network, at least by the standard of the year 1900. So that's kind of like an example of how you could like essentially navigate through a data set interactively and reveal progressively different and more information. Animated transitions, like most of these techniques that you just saw, like the table, for example, if you remember, there was like animation, right? It didn't just like disappear and reappear, but instead it had a smooth interpolation between the different data points. And the idea of smooth interpolation is that it makes it possible for people to track what's going on, right? So you can see the elements from like if you change an axis in a scatter plot, if you move your points in the scatter plot, you kind of get a sense of what was where before and where did it go. So that helps you keep track of items. It helps you understand the relationship between states. So for example, when we looked at this first in 3D and then from the top, right? This animation really helped that we understood what is the relationship between those two plots. But of course, there's limits to it, right? If I have a very large list, so maybe in the soccer table, it wasn't quite clear what was going on because there were so many things flying around off screen. Here's like an example of a hierarchical navigation technique. So this is like a disk that kind of like you can click on and it breaks out this sub part of the hierarchy and creates like an outer ring. And I think this is a fairly cool and intuitive implementation, right? So you can see that you can make a tiny segment and like take off the whole space. And it is also clear what is going on here. But there's, of course, limits on what to do this. And so this paper here studied kind of like the benefits and the drawbacks. And so I'm going to play this video here.
information using statistical data graphics, it is common to look at a number of related graphs. For example, the viewer of a bar chart may want to switch to a pie chart to view relative percentage. Transition to a scatter plot to look for correlation between two variables, or drill down by breaking up the data by category. Animation is one promising approach for facilitating perception of changes when transitioning between data graphs. Using design guidelines motivated by research in human perception, we have developed Dynaviz, a system supporting animated transitions for statistical data graphs. Dynaviz provides animations for a number of different transitions, including changes of perspective, filtering, and viewing changes of data over time. In some cases, changes of value require changing the axis scale. Here we show a sorting operation. Animating everything at once can result in items including each other. By slightly staggering the movement of each of the bars, Dynaviz makes the sort easier to follow. Here, a bar chart becomes a radial donut. By drawing the wedges to take up the whole circle, we form a pie chart. We can also perform drill down operations, breaking up the data further into distinct categories. We can then unstack the bars to view the same data as a group bar chart. Of course, we can always reverse the transitions to return to the view we started. We might want to compare different variables in a scatter plot to look for correlation. Here, we keep the y-axis values the same as the bar chart and use the x-axis to show a new variable. Animation is also helpful for showing transformations to scale. Here we show applying a base 10 log transform to the data. Both data and axes smoothly animate to show the results of the trend. Visual encoding such as shape, color, and size to be used to visualize additional data dimensions. To evaluate the use of animation in data graphics, we ran two controlled experiments. The first experiment asked users to follow two targets across an animated transition and click their final position. To better test how animation affects memory, we masked the display after the transition by turning it black. We compared static transitions, direct transitions in which all items animated at once, and stage animations where movements were split up over time. Our results found significant benefits for animation and found that stage animations split up movement through staggering or separate stages consistently improved accuracy. The one exception was for changes in a scatter plot, where two quick transitions in a row were more difficult.
So consistently improved accuracy, looking at this chart here, what would you say about that? Is that a fair statement to make? Just from like a data analysis perspective?
Better than static, but almost.
Exactly, right? I think this is a statement that nowadays a reviewer would probably not accept if you submit a scientific paper, especially if the effect sizes are that small, right? And it looks like, well, this way of reporting these experimental data is actually not pretty good. This is like an older paper. It's from 2007. Like people have moved on to better ways of reporting. We'll talk about this when we talk about tablet data. But here the error bars tend to be like, they show a fair bit of overlap between these experiments, right? And so we would have to look exactly at the paper, whether they did any like other tests. But that seems like a strong statement for this. So what we can say is that essentially stage animation doesn't seem to make it worse, right? And we probably all agree that it's cool. And so why not, right? Oops. That was not the plan. So now I don't get the YouTube menu.
Data graphic. Now, stage animations that set in 50% row were more difficult to follow than one longer transition. Second experiment asks users to follow. When analyzing transitions in a row or more animations, we split up movement display after the transition by turning it black. We compared stage animations, which split up movement through staggering or separate stages, consistently improved accuracy. The one exception was for changes in a scatter plot, where two quick transitions in a row were more difficult to follow than one longer transition. Second experiment asks users to follow a single target undergoing a change of value and then estimate the percentage change. The timing of transitions was slightly longer to accommodate some more complicated transitions. For stacked bar charts and donut charts, we experimented with more aggressive staging that separated translational movements from changes of value. Separate translations and value changes while also avoiding occlusion required a number of animations. Our results again found significant benefit for animation. Change estimation using simple staged animations that separated axis scale changes from other changes performed better than direct animations that combined both. The more complicated transitions for stacked bars and donut charts provided no benefit, arguing that the complexity of aggressive staging may outweigh any benefits gained from doing one thing at a time. Overall, users significantly preferred animation over static transitions, and furthermore, significantly preferred simple staged animation to direct animation. The overwhelming majority of users expressed the desire to use animated transitions in their own data analysis and presentation.
Okay, so just from this video, anything that they didn't seem to have tested? That's kind of obviously like a short, or not a shortcoming, but a limitation, let's put it this way. All of these examples seem to be very small, right? They seem to be like 10, 15 data points, right? So, and I think this is really the sweet spot for these kind of animated transitions. If you have like a handful of data points and you want to like really do some nice change in the perspective, like definitely doing something like this is cool. If it gets more complicated, right, it's really tricky to know what to do. And so I think there is a little bit of a, you know, you can read like where you should do this by what's also not done in this particular experiment here. So changes can be hard to track. And then there's like one principle that's called eyes over memory. And that's very important. And I'll come back to this a few times. But essentially, every time you show a transition like this, you also have the option of showing just a second view at the same time, right? Of course, that needs more space. But depending on what you want to show, it might make sense to just show two views. And so, for example, in the example of the railroads, what we could have done is we could have shown, like, here is the, like, you know, at some significant point when the railroad was being built versus at the end of it. We could have shown those two plots. Then people could use their eyes to compare between those two sides, right? It might be hard for them, for anybody, to memorize like what happened in the first stage, what was there before, right, versus what is there now. So this is this principle that if you want people to make explicit comparisons, you perhaps better show them both of the things that you want to compare at the same time, instead of like making an animated transition or any kind of transition between them. Okay, so we can use interaction also for navigation. And navigation, there's like 2 or 3 main things that you want to do. You want to pan, you want to zoom, and you want to rotate. The simple example that we are all familiar with, of course, is something like Google Maps. Like in Google Maps, you're all familiar with panning and zooming. We don't typically rotate because we tend to like that our like that maps point up north, right? But I can like zoom out and I can like pan here at like at whatever with whatever level of detail I want to. And that's kind of like a super intuitive interaction. You also have this for touch for gestures, right? You can like use this kind of like pinch gesture that we know from phones, and you can use them now on computers too. And so that's kind of like the simple kind of like 2D or 2D projection case. And then, of course, if you have real volumetric data, your interaction becomes a little bit more complicated. This here is, I think, an Fmri data set. And so what we have here is I can actually, like, you know, rotate this object. I can zoom into any part that I want to. And you can already see that zooming here is a little tricky, right? I'm zooming in too much, maybe a little bit. And then we have all of these issues that we have with 3D navigation. And then we also have here some like 2D slice navigation. So this would be kind of like more or less like 1D navigation, actually. Like we simply navigate in this 2D plot along a 1D axis. And so these are the kinds of interactions that you use frequently for navigation. But of course, we can also use navigation in like an abstract way. So navigation in the previous two examples was extremely literal, right? It was like for navigating spatial data, but we can also navigate a story. So for example, we can use the technique that's called scrolly telling, and that's something that's very common because it's very friendly also for mobile user interfaces, right? I don't have to like click any buttons or anything like that, but I can just swipe. And so the interaction here happens by scrolling. And so here is one nice example. This is what is really warming the world. This is kind of like, you know, essentially here first we see and the observed temperature record from 1880 to 2014. And now we can kind of like do some eyeballing. Are there any correlations with any other factors we know about the world, and see whether there's any correlation between them? So we can, I mean, I'm simply swiping here, right? And so now the first question is it the Earth orbit? Maybe the Earth orbit is changing, and we see that the orbital changes here tend to kind of like remain static over the time periods, more or less. Is it the sun? The sun temperature varies over decades. This might have an effect, but it actually doesn't seem to be causing it. Is it volcanoes, right? And then we see kind of like the effect of volcanoes here, and we can continue swiping. Is it all three of those things combined? And now like they are plotting the expected change here, so that the natural factors that come up here. So could it be deforestation? And then like they're plotting how is deforestation affecting the climate, or is it ozone pollution? And there's a plot of how ozone pollution does it, and so on, or aerosols. And then if you look at greenhouse gases, of course, we see this correlation, right? But the nice part about this from like a visualization perspective is we have this very complicated data set. Like this could have all been plotted in one single chart, right? Like I could have done this all in one chart, but they chose to layer it. They chose to tell you there's always like a little bit of a story here at the beginning. It's like the main point, some details, an animation that makes it appear, that grabs your attention, and then a very simple interaction like for navigation to move to the next part. And so here are all of the factors combined, and then you can like actually, this is also kind of a cool, like we'll see this in the storytelling lecture. It's a cool technique that if you first have some guided interactive story, you can, at the end of your story, you can kind of open it up for exploration, right? So you can let people investigate for themselves and play with a little bit more freedom, as you can see here. Okay, so the next thing is semantic zooming. And semantic zooming is kind of a cool technique that's not, well, I think that's super easy to implement, but it's not, I haven't seen it as much as I would expect. So the idea of semantic zooming is that you have, like, you zoomed out. And then when you start zooming in, things not only get bigger, but you get more detail. And I think the most successful implementation of this is obviously like a Google Maps-like interface, where you start off with like a map of like the major countries in the world and maybe some mountain ranges. And as you zoom in, you start to see highways, and then you see streets, and then you see shops and so on, right? And these are all dynamically added. And that's what's called semantic zooming. Content is updated as you zoom in. And this is ideally readable then as multiple resolutions. And so you all notice from maps, but this is also works just as well for other techniques. And so I'm going to show this video here.
Interactive visual exploration. Time series. We show live visualizations of large quantities of data. Domains and management. Monitor devices are represented by rows. This label shows aggregated information about a group, NFS, or devices. Columns show one or many parameters collected from the devices. This column shows CPU usage. In the current overview, each cell is a small colored block. In these 4 cells, pre-mean CPU utilization is above 35%. As I make the cells larger, labels for the individual devices become visible. Also, when the cells get big enough, the server is queried for more data, and then the representation changes. Blocks is part blocks. Making a cell even bigger results in semantic zooming. Show a more detailed line graph. You can see the current time range by looking at the time boxes.
Notice this transition here. That was like, first it was kind of what's called a spark line, so just a line that didn't have any axis labels, right? Because it's very compact. And then suddenly when it's big enough, they add labels for both axes and also labels for like what do those lines in here mean.
The bottom left and bottom right of the data area. Blue lines show progressive search results. I'm searching on NFS. Find the devices I've already stretched out.
Okay.
Pretty network environment state.
Okay, so another technique is focus and context. And that's kind of like the idea is that you carefully pick to show and at the same time hint at what you're not showing. So like you have focus elements and context elements. And so it's kind of like a synthesis of visual encoding and interaction. Like a user selects a region of interest, which is kind of the focus through navigation or selection. And then you provide context through aggregation or reduction or layering. And so this is the classification that Tamara Ronson makes in her textbook here. Like what are the different ways we could provide focus and context? And the first one is elision, data elision. So providing like basically tooltips here, superimposition or distortion. And so we'll look at those in some more detail. Elision is a word that you might not be familiar as like if English is not your native language, it wasn't familiar to me until I read this textbook. It's basically the idea is the focus item is shown in detail and other items are summarized for context. And like one example of this would be this space tree technique here. So you kind of like, you see some hints that there is more going on, and then you can click at them. And as you ask for more information, it is being added to the tree, right? So this is kind of like the same principle that we've already seen here. And now in this case, we even have like search here. So that's basically this information is dynamically added as you need it. And there's one interesting kind of concept behind this idea of elision is this degree of interest function. And that is kind of like based on the observation that humans tend to represent like their own neighborhood in detail, yet only landmarks for something that's far away, right? So like if you think of a navigational perspective, it's you know exactly the streets around here, but you might know roughly where the other big cities are in the environment, right? But you like if somebody asks you to like, well, what's the route to Vegas, right? You will just point them essentially south, right? You're not gonna like have all the detail here. And so the idea for visualization is here that we have this degree of interest function that is composed of two different terms, the a priori interest and a distance function to the current focus. And so if we kind of like play this out with the map example, right? If I were to draw a map of Utah using this degree of interest function, there might be this a priori interest of things that I would put on that map. This is like big cities that are important, right? For example, Las Vegas and Denver, they have like a high a priori interest. But if I am local, like here in Utah, I might even consider adding things like very close by coffee shops or anything like that, right? That would be my distance function. So like basically the idea here is that where you are, show the neighborhood in detail, and then for everything else, show the very important things, right? And that's kind of like what this function here combines. And so this is like, for example, implemented with DOI trees. This is like an interactive tree with an animated transition that fits within the bounded region of space. And the layout depends on the user's estimated DOI. So you could use this for logical filtering, geometric distortion, or semantic zooming based on node size or aggregate representations. And so here's another video. So this is a hierarchy, and it kind of like, shows you some more details depending on how important something is, but also in where you are in terms of the navigation here. You can also use a DOI without a distance function. The distance function can lead to very big involuntary changes, right? And so like we had here like an example, this was a paper where we played around with like a distance function, with a DOI approach without a distance function, so that we would always see some context for like nodes in the graph. Okay, so to recap, the idea here was that if you want to group like a lot of elements, right? Some of them might be more interesting to you. Like in this case here, we're looking at researchers in the papers, and we're making an assumption that papers that are cited frequently or researchers that publish a lot are more important. And if we group researchers in some sense, we might want to show these are 3 important representatives of this class, and everybody else here is summarized. And that's kind of like the idea of this paper. So here you see kind of like for each of these groups here, there's like one person, and then there's like many other people or many other papers in this case that have some context. Okay, superimposition is basically you combine 2 different visualizations on top of each other. You have a focus layer, which is limited to a local regional view instead of stretching it across the entire view. And then like that's kind of like something that we'll be looking again when we talk about tablet data, for example. And then finally, we have distortion. And so geometric distortion is kind of like the idea that, you know, if I have something like a map, I could do these kind of like provide this focus and context such that I kind of like show you the things that are close to the center in much detail and distort everything and make it really squishy and small, but if it's further out. And that's been kind of like heavily researched at kind of like at the, like I would say in 2000s and a little bit later. So here is an example of like a theme river visualization that uses this, this distortion. And so you kind of see here, these lines indicate like the distance between each of those lines here that go here indicate a similar or the same time span, right? And so you can see that this time span here is actually equal to any of those time spans in between those lines here. But this is not a focus region, right? And so you kind of see that at this moment, these are kind of like some of these the examples here. People's emotion, right? How did they feel? Happy, tense, upset, sad, calm, serene, relaxed, and so on. You can see at this moment there was lots of happy feelings, and so you can kind of like see the details about this moment, and then you could navigate further out. You could also like do something like this in a slightly different way, maybe a little bit more with this DOI function or with summarization. This is kind of like an alternative to this. Instead of using distortion, there's smart aggregation. And so here the idea, I think this is the best example. This is like a line chart for the focus region, but then there's context pieces here that are summarized with like a histogram, right? Histograms give us like an idea of the distribution of the data. So instead of showing some very like squishy lines here, they tell us, okay, it looks like most of the data in this context region tends to peak around this bar here, and there isn't really like any big high outlier. So that's something that we can immediately read from this chart. And so this paper won an award a couple of years ago for like this idea of providing the smart aggregation instead of geometric distortion. The most popular implementation of this is kind of like the fisheye view, this geometric distortion. And so like the idea of the fisheye view is that like basically you have something like a rubber sheet, right? And you stretch it out, and then the things in the middle that you look at are shown enlarged. And so you have this kind of like function that is like, here's the magnification factor on the y-axis. And so it's very high, then it drops off, and it actually goes down below what it is if it's neutral, if it's not magnified, because somewhere you have to make space for that, right? So you have to squish something around this around the periphery. a little bit, and then you have your like essentially normal magnification as you go further. And so this is like an old video here that explains this principle.
Notice how outside the panel, distortion falls off the distance from the collection. Another reason. Yeah. Reform this scale, preserving distances where distortion happens.
So as you can see, this is like an old video, and you probably haven't seen all that much of this system in real life. This has been also used in these like hyperbolic trees. This was kind of like a big hype and end of the 90s, that you have kind of like hyperbolic geometry, and that you could kind of like endlessly navigate a tree like this. And so this would be an example of that. This was from
tree browser, a focus on context technique for browsing large hierarchies. Here we see a recent bar chart of zero containing over 300 nodes. The root of the tree is at the center of the circle, and successive levels of the tree are closer and closer to the edge of the circle. The edge is kind of like a vanishing point. Spacing gets smaller and smaller as those approach the edge, but the entire tree is displayed inside the circle. The structure of the tree is prominent, even when some nodes are too small to display text. For example, staff positions can be distinguished from line positions. By clicking on a node, we bring it into the focus area. Thus, we can see more of the detail of that part of the orchestra while maintaining the context of the whole. We can also grab a point of the space and drag it around to the right. To achieve crisp dragging and to keep transitions under 1 second, rendering of the tree is degraded in a couple of ways. Notice that the arcs are turned into straight lines and less of the exponential fringes change. The hyperbolic browser, like other focused on context techniques, deals with the shortening of screen space by showing more about a few amid a little about many. Here we use wafers to show the amount of space available for node information. Notice how nodes grow as they approach the center and shrink as they recede. We can interactively adjust how space is proportioned, say perhaps introduces of spatial socialism. The hyperbolic browser can support other types of hierarchical data sets, e.g. part assemblies. For some applications, an alternative layout works better. Here we have the children of the node in focus standing out to the right. As a new node is clicked on, the structure rotates as necessary to orient that node's going to the right. A particularly interesting application area.
And here's like finally a video. This is like a little bit more recent that I'll briefly show.
With data provided by the Land Transport Authority, it's possible to monitor the activity requested for applicant form, but considering the large volume of information, exploring individual bus stops is a challenge for visualization. In order to achieve this, experiments has been developed. It acts like a magnifying glass around into explore with great detail the activity of the bus tower. This magnifying glass distorts points in space.
So what do you think about this? Okay. Any reasons why I don't like it? Yes.
But it does make everything around it.
Exactly. That's the problem, right? That what you see in the center, okay, but everything else is kind of hard to track. Yeah. Yeah, and so this is kind of like the big problem with this hyperbolic geometries, right? They like it tend to works kind of cool in some for some aspects, for like one-dimensional. If you can do this, if you can manage this kind of like gradation, is not in this navigational overhead. So here are two examples of like a list view, right? This is like a very compact representation. If I click here anywhere, I would get this in detail, and like this would be like ranked universities, right? And I would see all of the neighbors. And there's like a similar idea here for a tree. And these are kind of like, they have limited complexity, and that's why I think they work. But if you have 2D already, you get a lot of complexity. So distortion tends to be kind of like unsuitable for relative spatial judgment, and that's really problematic if you want to show a map, right? Like if you suddenly can't do spatial judgment anymore on a map, then you have done something wrong. And there's kind of like this overhead, even though it's nice that we are able to focus on some elements, there's this mental overhead of tracking the distortion. And we have to visually communicate the distortion. So for example, we have to add grid lines or some shading or anything like that. And then we have what's called the target acquisition problem. So the lens is displacing items. So I actually don't know exactly how I need to move my lens to get a particular item into focus, right? At least if I have like a continuous zoom with the lens here. And so there's like people like research this heavily in like the 90s and beginning 2000s, and then developed many, many techniques. And then they started doing studies on it, and studies showed that it actually, people didn't do well with it, right? And so it kind of like this kind of whole branch of research more or less died off. And yeah, probably for good reason. So here is kind of like a very cool idea. This is like a maybe a little bit niche, but I just love the principle. Anybody read Calvin and Hobbes as a kid, or more recently? Yeah, you remember transmorgification, right? So he can basically step into a box and be whatever he wants to be. And the idea here of these guys, this is like a group from Calgary, they want to be able to transmorgify shapes, complex shapes in image space to something simple. And for example, what they show here is like they trace rivers, like the Colorado River or something like that. They trace it, and then you get like a linear representation of the river and its neighborhoods. And so I'll show like this very nice video, because like the cool part about this technique is it works in image space, and you can do like a lot of cool things in image space. So in here, in this case, you can map like the linear path to a circular path, and you can link it. And so they use it up to this point for maps, but you can actually also do it to use it for some transitions between charts. And here, like transforming a rose petal chart into a bar chart. Okay, so this isn't something that is super useful in practice, right? But it's conceptually amazing, right? It kind of like shows you the relationships between all of these objects. It could be kind of like intriguing in like an artsy or museum context, right, where you can play around with something like this. And like, yeah, I just think, and especially I also like that this is all done with touch and super simple interactions, right? So it's kind of like a very nice prototype. Okay, so now I want to talk a little bit about overview in detail. Any play Warcraft? This here is a screenshot from Warcraft 3, right? And so like my generation of video games, it's a little bit older already. Basically, like what you have here is one view here gives you the overview, that's the map view. And then one view gives you the detail, right? That's like where your character is. And you can apply this in visualization. Until a while ago, Google Maps did still have that, right? So like nowadays, if you look at the newspaper and if they, for example, show you a map of the Ukraine with some detail, like where there's some fighting or so, they might also show you like in a small inset, they might show you a large, like a scaled down version of the map and kind of tell you where that cutout, where that detailed piece is, right? And that's the idea of overview and detail. But tooltips can also provide detail. So for example, like we've implemented tooltips very simply, right, with the HTML title attribute in our homeworks, for example. But tooltips can be sophisticated. So here is kind of like an example on the left that is a tooltip in Tableau. So if you like click on a state, like Minnesota in this case, you will get actually a tooltip that shows you more charts about that state, right? So you can provide arbitrary much information in a tooltip. And this kind of goes back to this Film Finder project that first introduced this from 1994. And so here you have movies from like the 60s to 95, and then you have their popularity, and you have a color coding by the genre. Is it a drama, mystery, and so on? And then wherever you click, you get more information about it, right? So that's kind of like the principle of tooltips, and like that still holds, and we still use this. Very similar to this is filtering and dynamic querying, or similar is the wrong word, but you know, similar results is what you can get by filtering and dynamic querying. And filtering and dynamic querying is often also called brushing or selecting. This here is Ben Schneiderman. He's now a professor emeritus at Maryland, and he did like, this was one of his projects here. And he is also like very prominent in HCI, but he's also very prominent in Viz, right? He's the most cited Viz person out there. And he kind of developed this visualization information seeking mantra that he calls like overview first, zoom and filter, then details on demand. And he continues it with relate, history, and extract. But the kind of like the first three lines here are this kind of like data exploration paradigm that people have really adopted, and that people really emphasize like in many papers. So like if you have a data set, first show roughly what's in it, let people dynamically, interactively zoom and filter in, and then provide details about anything they find interesting on demand. Of course, this isn't the only thing, and it's not always the right approach, but in many cases, this can be like the right approach, and it's very definitely worth considering when you build a visualization system. And so he introduced this dynamic query system. Like remember, I talked a little bit of some of this today, but first I will, dynamic queries is essentially like you have something on the screen and you want to dynamically define criteria for inclusion or exclusion of some elements. Like you might notice from faceted search. So for example, if you're looking at the new TV on Amazon, you might say it may cost more than 500, but less than 2,000. I want at least 30-inch, but I also don't have space for 60-inch, right? So you make these kinds of restriction with faceted search, but this all comes from like the visualization community as well. So here I'll show this old video that actually Ben Schneiderman himself narrates. And this is also what we'll be like doing an interaction design activity right after I've showed this video here.
And again, the principle is to visually demonstrate query components and the results and provide rapid and immediate feedback. For that, I'll take a look at the demo here on this display. Let's move over to the side here, and we see on it a map of the Washington DC area with the Potomac here. And this is an improved version of where we were a year ago in terms of dynamic home plot. The scenario I present to you is that we're coming up on the new administration, taking a job with the Clinton administration, and your spouse is going to be working at the University of Maryland. You're looking for a home. So the first thing to do is to mark where you want to work here at the University of Maryland, right about, I'd say there, A marker. And then your spouse is going to work downtown in the executive office building, right about over there. Marker. Okay. And now each of these points of light on the display represent a home for sale. And if I move to the right, I can control this display by choosing the distance that I want to be from point A. And now it's set at 30 miles, and I'm going to bring it down. You can control rapidly, incrementally, and reversibly the distance that you wish to be from point A. So let's say you decide, you see there's plenty of that. So you say you want to be, let's say, 5 miles from work, so that you could, let's say, bike to work. And now you want to be somewhere inside that range from B, so you slide down and you now can see the set. And this is, looks like we've got 40 or 50 homes over there. If I now choose about the number of bedrooms, I really want 3 or 4 bedrooms, so I move this double box slider to be 3 or 4. I've still got about 30 houses on the display. So why don't we look at the price now, and we want to keep the price down, let's say about 170,000, between 140 and 170,000. And that's given us a set of about a dozen here. We can trim a little further by choosing, we can choose some houses, townhouses, or condominiums. Eliminate the townhouses, condominiums. So we're selecting only houses. Yellow indicates selected fields, and I can see now I've got about 10 of them. If I click on any one of those points, if I just click here, then the bottom of the display gives me a description of that house, home park, a newer middle class neighborhood, colonial brick, and fireplace garage, etc. This gives you a way of posing a very specific query, seeing feedback immediately, and getting an answer to your question, plus reformulating your goals as you see the result of this query. Now, enough.
Okay, so that's kind of like the idea here, and I now want you all to like take 15 minutes. So we'll use the rest of past time more or less for this activity here to think about this, because one thing that we did, what he showed here, is he used these sliders, right? So I want you to think about how could you change this to direct manipulation. Remember in the beginning, I mentioned that direct manipulation is kind of like the better way of interacting now. And now take this example, but try to think about that, like how can you add direct manipulation? And then also, I would like to be able to apply different filters for different areas. So for example, I might be willing to accept a higher price if it's closer to downtown as opposed to the suburbs. And then I also, like, you know, these sliders, they're not particularly smart. They don't tell me exactly how much I will have left. And so I would like you to think a little bit about how you could show the distribution of homes available for each variable. So are most houses 7 bedrooms or 3 bedrooms, right? How could you integrate all of this into one interface? And so I'll hand this out, and then like 5 minutes before the end, we'll talk about some of your solutions or show you a reference solution from myself. What's that? You know, when you can integrate it, there's probably never a real reason to not use it, but sometimes it might not be easy to do.
I just have to control there's no I want.
I would say that not everything can be done with direct manipulation, right? And like if it's not possible, it's not the right choice. But here, like I want you to think which variables are good for direct manipulation in this case here. Okay, so anybody want to briefly describe what they came up with? Maybe let's talk about direct manipulation first. Which variable did anyone choose for direct manipulation? Distance. And why did you choose distance? Exactly. So we already have like a nice plot in for the distance for geospatial location, right? And so having this like a radius that you could drag around the point would be like a cool way of doing direct manipulation. Anybody chose any other variables for direct manipulation? Yeah.
The other one could be like you would have to put in icons or shapes or something for color for the like optional house townhome.
Yeah.
And you can just click on it.
Yeah, that's a cool idea like that. So we have categories for different types, and we could kind of like indicate by clicking directly on them. Like I'll right click on I don't want a townhouse, for example. Yeah, that's a very fancy way of doing it. That wasn't possible back then, right? Because it didn't have like a nice Google Maps interface. But there's these cool maps now where you can see how long it takes you to drive from a certain location, right? So that's a nice idea. And how did you like solve the second problem, like the or the first problem? No, let's do the third problem first. That's kind of the easy one. Did anybody thought about how we can see the distribution of homes? Yeah.
Where they fall inside our.
Yes. Yeah. Yeah. Okay. So basically, you would be kind of overloading our channels. Like we would add additional visual variables or additional channels on top to indicate. And that's a good idea. Anybody else came up with a different one? Yeah. Yeah, exactly. So basically, a histogram could be a tooltip. I kind of sketched this as making these kind of like called scented widgets, right? So I always show the histograms in my design here. And so instead of the slider, I have a fancy slider that shows you the background distribution, right? So that you have a similar one. And I also have this kind of like same idea of like direct manipulation of the places here. Anybody tried different filters for different areas? I'll ask somebody else maybe. Yeah, over there.
Just like an Adobe tooltip where you got like a pencil, have like a polygon stuff, and cycloid stuff, even different like this.
Okay, so if I understand you correctly, you have kind of like a not a circular filter in the end anymore, but some kind of like interesting shape filter. Cool. Good.
Yeah, that's like snap like some sort of shape that is fitted into that map that also they did that as a double.
Yeah. Cool. Up there.
Using multiple circles or
Yeah, this is exactly kind of like what I did here, right? You see, I have this A and B1 price range here, and my B2 price range. So, for example, maybe my spouse has to accept long travel times if we get a cheap house, right? That's kind of like the principle here. So yeah, cool ideas from everybody. Thanks for participating. Just want to say, like, 2 more slides before we end this lecture today. These kinds of visual queries are super powerful, right? And we can use them on scatter plots or anything like that, but we can also use them on other plots. So here we have a parallel coordinate plot, and a plot like this really lives from these interactive filters and this kind of like dynamic highlighting. And you can do this, of course, in arbitrary complex configurations. So you can have multiple combinations of filters. You could even do this for 3D space. So for example, here, like you would have like a box that is kind of the brainstem probably, and you only want to filter all the paths in the brain that go through that particular box, or more complicated examples on the, as you see on the right. And then I'll be talking more about filters in a future lecture because it's such an important principle. And then I'll see you all on Thursday for the exam, and then we'll have no lecture for 2 weeks. I'll say have a great fall break already because we won't be talking too much during the exam. So thanks, everybody.